What I didn't mention at the time was that all of the first branch is stable, the other branches are unstable. Why are they unstable? Because they're born of an unstable parent, and everybody knows that if your parents are unstable, you're going to be unstable too. You better do something to get your life right. Let's show that in pictures. Here is your original state. This is the origin. It's got no convection. It's got no features. It's stable in all directions. Okay. Now it's going to have children here. It goes unstable, and it has two. You've seen this picture now many times. Okay. This is an eigenvector. The amplitude of this eigenvector with the QC is represented this way. Now, so that's what happens at first. You see that it's once unstable in this vertical direction, and the new guys are stable. They have 0 unstable directions. That's what these numbers are telling you. Now, a second eigenvector goes unstable, and it's represented along this horizontal direction. It's horizontal. It's another eigenvector because it's got another cube, and you know that different Fourier modes are all orthogonal to one another, and that's this another cube. Another cube here. Remember I said that at each time mu hits some q, you have a new branch forming. But that's a different cube. It's orthogonal to the first. E to the iqx is orthogonal to the first. So that's what's happening here. It's now going to have it goes unstable to an eigenvector in another direction. So it gives birth to new children. But this is the phenomenon I was saying. The parent here was unstable in the going top and bottom. You see how this guy is unstable. It has one unstable direction already as a parent. When it gives birth to 2 new kids that are like it, unstable in the vertical direction, going up and down, and stable in the horizontal direction, just like it. Just as these two resemble their parent before it gave birth, so too these two resemble this parent before it gave birth. Does everybody see that? Now, I have to say, a lot of people do not know this. You might think this is very simple, but you will go out in the world and you will draw a bifurcation diagram, or people will draw bifurcation diagrams like this, and they will think that all the branches are stable, and if you say, oh no, they're not, they will say, why is that? And you can go through this whole explanation of the bifurcating branches inherit the instability of the parent. And so here, what we would say is, we've drawn many times this branch as being unstable, right? We know that and that means that this new branch is unstable as well. But not just that, it doesn't stop there. We see that the parent now has become twice unstable. It's unstable to it has 2 eigenvalues in its Jacobian that are positive. It's unstable to going vertically, going e to the iq1x, and also going horizontally towards e to the iq2x. Both of those perturbations grow on it when you get to this mu value here. Okay? It can then, let's jump to this picture, forget that one for the moment. It can even, the Fourier space, after all, is infinite. Our physical space, we're poor mortals, we're reduced to just understanding things in 1 and 2 and 3 dimensions. But Fourier space is infinite, or phase space is infinite. There's an infinite number of directions, infinite number of Fourier components. So it can also go unstable in another component, in another direction, which is here, in which case now it has 3 unstable directions, this way, and that way. And that's what's drawn here. It has a 3. It's gone unstable in 3 directions. When it made new states here, its new states became inherit the instability of the parent, which at this point was just 2. The children at this point are doubly unstable. So you just see that over and over. You see here that this 0 is the inheritance of this 0. This 1 is the inheritance of this 1. This 2 is the inheritance of this 2, and so on, all the way. So naturally, you might think you could never see anything other than the first branch. But that's not true. What happens, and we saw it already, we saw it over here. We saw it when this eigenvalue, which was positive, decreased and became negative. That is to say, what's going to happen, these pictures is this state here. Remember, it's once unstable. You see it. You see how it's once unstable. Here it is over here. Oh, it's become stable. How did it become stable? It became stable through a subcritical pitchfork bifurcation. It was, from the point of view of this one, let's draw it. It was unstable, and now it's going to become stable and have, okay, you've seen this picture before. You've seen this picture, right, of the subcritical bifurcation. Hold on, I'm doing something wrong here. Just a second. Just a second. I'm not doing this right. These branches go to the right. You've seen this picture. Now you've seen this, and then this, and then this. This is one of the 4 pictures you saw in pitchfork bifurcations. And that is what you see here. This one here, he gets to stabilize by emitting 2 other branches that absorb its instability. Just in the same way as before, these new branches inherit the instability of these in just the same way. They were vertically unstable and horizontally stable, and that's what these guys are like. But meanwhile, this one has become stable. Okay, everything adds up with the arrows? I mean, I'm only talking arrows, but you can do computations and you would find the same thing. Those computations are on this previous picture here, previous slide, but it's too late for. Okay, so I'm just telling you that this is what's happening. This one now is stable, so he's drawn with a 0, and you see these new branches here, that's them. Okay, so now he's stable. So you started off with a situation where you had one stable state, then you went to a situation where you had a single branch, with a certain wave number here, and your original state was unstable. And now, by the time you get here, you have 2 choices of stable branches. You could be here, or you could be here, above here. And this point here is called the Eckhouse instability. And you can see that this continues. I mean, I drew it continuing. That is to say, these new ones here that are twice unstable, what do they have to do to become stable? Well, they have to make children this way, and they have to make children this way. And they do that in 2 successive bifurcations, here and here. They become stable against one of those 2 directions here, and then they become stable against the other direction here, and they're down to 0. And now, starting from here, you have 3 possible states that you can be at. They're all stable. This one, and this one. Okay, so this is telling you that for low supercritical Rayleigh number, you have only one choice of wavelength. But by the time you get here, you have 2 possible wavelengths. And by the time you get here, you have 3 possible wavelengths. And it also shows you that existence is not the same as stability. These branches are born here and here and here, but they don't become stable until here. They're here and here. They are born unstable. And most people don't know how to reason in this way. I mean, it's simple enough with arrows and all. And you might, okay, don't think it's not rigorous. Let's say you can back it all up by doing calculations and linearizing and taking the Jacobians and all that. This is perfectly rigorous, and most people do not know this. And that's what's being drawn here, is as you go up, you run into a stabilizing bifurcation and another stabilizing bifurcation. Here, this is the branch that had one stabilizing bifurcation and then another one, because this one was born, this one was born stable. The next one was born once unstable, and it's below one of these solid parabolas. This one was born twice unstable. It had to go through this one and this one to become stable. And each of these parabolas, they are just this formula here. They're this formula for Q fixed, a K variant, K taking integer values. And so I can show you now films of the Eckhouse instability. And then we'll be almost finished. We have just one other thing that's just like this that'll take no time. We'll go to Safari. We'll hope that things are good. Let's go back. Eckhouse instability. We're gonna have to start it over. I think so. I'm glad you told me that that's all I had to do. Yeah, so I already quit. And why do you think that is that I have to quit? I wonder. So start again. Let's see where it was. But now it's white instead of gray, and Java turns around, and I say run. Yay. Okay, so I'm going to start it. Notice there's no G1 here. There's not that, there's no hexagon. This is that roll. Remember G1 being final. Okay, so let's start it. Let's start it. Yeah. There. Okay, so what is this Eckhouse instability? Eckhouse instability is when you start off at the is when you start off here, say this wave number. Remember, this corresponds to some Q, and it's okay. But you lower the Rayleigh number, and then you get here, and it's not happy, and it wants to change to one of the Qs that make it happy. That's what Eckhouse instability is. You create one with the wrong Q, and it goes, and it becomes happy by changing its wave number. So let's do that again. Start. That. Okay. Now let's look at it in Fourier transform space. Okay, so you see a perfect system of rolls has these as e to the iqx, e to the minus iqx, right? Everybody agree with that? Now let us start again. In Fourier transform space, we're going to look at the look at the transition. Okay. So we see it's got its perfect rolls, that's fine, but they have the wrong wave number. You're going to see that in just a second. There, it jumped. I guess I should make the speed less. Maybe this all was done at a time when computers were so much slower that you could see something happen. Let's start it again. Watch those wave numbers. Up. Now here, this is the Eckhouse instability, but it's done more realistically. You don't have perfect straight stripes. Let's start it. You see it have it, and then it has to straighten itself out. And you saw that before, how it has to straighten itself out in the end. If I make the speed less, I don't think can I make it a non-integer value? I wonder. No, it's not happening. Stop. Let's watch it. There. Now let's watch that same transformation in Fourier transform space. So again, we're starting off with a system of perfect rolls. Not quite. There's a little bit, it's got some little imperfection in it. I don't think you can see it's too small here. And let's start it. And very soon it goes to that. That, what you should be looking at is that it has a different radius from here. It was pretty much at the same place horizontally, but it moved in such a way it had a different radius. The radius that it's, so now hold on, that should be perfect rolls. There shouldn't be any problem with that. Yes, it's perfect rolls. But sometimes because it has a small random element in it, so it happens differently each time. Let's go back to, let's do reset. Let's look at Fourier transform. Let's see if we can do something, because this here it didn't get stuck. Let's do the one we just looked at. Let's look at one where it does get stuck. Start. There, now it's a little stuck. You see all that fuzziness there? Stop. Let's see what it looks like with that fuzziness. Okay. And now it's going to straighten itself out. Okay, we do just one more thing, and, oh no, I know, before that, hold on, while we're still here, let's do, let's do, yeah, we did these demonstrations. I told you that the script homework could form quasi-patterns, even one like that. And look what's happening here. Over here you have a cubic term, and quadratic term. I guess you need them both, I think. But look what you have here. Here you have two different wave numbers. Before you just had Laplacian squared plus q squared, or Laplacian squared plus 1 squared. Now you have both of them. So you have a wave number that's q and a wave number that's 1. Okay? And we know that quasi-patterns are a result of two different wave numbers. Let's go. There's two wavelengths here, one that's like this and one that's the little one. And this little tiny equation just does that. Let's do it again. I think we can do it again, because I think it starts with a random initial condition. It'll be slightly different. But it's basically going to be the same thing. Let's look at it in Fourier space. Let's look at the pattern. You see there's this wave number and this wave number. A little one and this one, Q is about 2. So that must be 2, and this is 1. But you see the discretization around the circle. Those are that's affected the nonlinear terms. Linear stability analysis would tell you that you could have anything around this circle and anything around this circle. But that's not true. That's kind of what we saw with our little calculations. You can't just have any either the IQX. You can only have square patterns or hexagonal patterns, or in this case, quasi-crystalline patterns. Let's look at what it. Right, isn't that pretty? Okay, so we're almost finished, very almost finished. Just in case something goes wrong with the demos, let me show the last demonstration we saw at House. Let us look at the demonstrations for the zigzag instability. That's the very last thing. Okay, let's start it. You can see why it's called zigzag. It's going to spend a long time like this, but eventually it's going to figure itself out. What it wants to do is be rolls, but with a different wave number. This is a path there. Now it's going to be happy and stay here. From this, you conclude that the zigzag instability is supercritical or subcritical?
Super.
Because
It wants to transition gradually to its final state, so the energy slowly becomes in that direction.
Okay. Anybody else? Any reasoning? A supercritical bifurcation looks like the original state plus the eigenvector. Plus what it started to do. It does something. What it would do is it would do this and then form a saturated amplitude of it. It's going to go to something completely different. When you go to something completely different, that's subcritical. When it's supercritical, you go to something you have some eigenvector here and you grow up to this and the amplitude changes. When it's subcritical, when you leave here, well, you don't know where you're going. You're going to some completely unrelated place. There's nothing related to the basic state that's stable for you to go to. With supercritical, yes, this is kind of related to the basic state. It's just a little bit more. It's this plus some perturbation. But here, it's going someplace else. And that's what's happening here. It's going someplace else. Maybe that wasn't totally obvious. Okay, let us look at the zigzag, and let's look at it in Fourier space. So see it form here. It doesn't like its wave number. Its wave number is here. It's whatever this is here. It doesn't like it. It formed little side bands, and those side bands are in the other direction, are perpendicular. That was the zigging and zagging. And now, okay, now it's happy. It's happy with this. Let's look at it. See, it's nice rolls, and it's happy with that. It has a different wave number. It has the right wave number, the one it likes. Before it had the one that it didn't like, but the way that it went to it was by doing this thing with the waves. So that's the original wave number wasn't here, and now they're component that's in that direction. That's what you saw with those things. Okay, so let's get back. We're almost finished because it's just like the Eckhouse except just slightly different. Our eigenvectors now, you recall we had alphas and betas with e to the I qx plus kx and then beta e to the I qx minus kx. Now we're going to have plus my and minus my. And we're going to do the same thing. We plug in this form into this equation. Before we didn't get to use this dy squared part, but now we do because our eigenvectors now have that direction. So we plug into there, and so when we do this part, we save it keeps the same wave number dependence, right? And when we do this part, it keeps the same wave number dependence. But we remember that we have that A star term, and that's the reason why the A star term is going to turn this into this and this into this. So we have AQ squared, capital AQ squared. Remember that looks like e to the I qx. That was our roll. We square it, so we get 2qx. This guy now, we're going to complex conjugate him, so we have minus qx minus my, and qx minus qx is going to give us qx, and then we have the minus my, so we're going to get qx minus my. That's the alpha star, but it has the form of a beta. So this is what's going to appear in the beta equation. Similarly, when we do this to the beta guy, we have 2qx minus qx, that gives us qx, okay, and then we have a minus minus my, that gives us a plus my, that's the form of the alpha, so the beta has turned into an alpha-like thing. And of course, the sigma term just keeps its own form. So now putting everything together, we have the d by dt, which brings down the sigma. We have the term, this term here. Excuse me, we have this term here and this term here. Right, let's see, we have a, let's go back to the equation. We have a mu. Okay, this term, and this term are not going to flip the alphas and the betas. We're going to have a mu, then we're going to have a minus 2, this term, and then we're going to have those derivatives, and that gives us that's the d by dt. We have the mu, we have the minus q squared, we have the minus m squared q plus m squared over 4. That stays the same. But then we have the flipping term that's over here, and that gives us a matrix. These terms here live on the diagonals, and these terms here live on the off diagonals. And again, we're going to find the eigenvalues of this 2 by 2 matrix, which is not as hard as it would seem, because all you have to do is average this, and then, and since they have the same, it's just this, and then we're going to take the difference, and that's going to be 0, and then we're going to take this, and okay, well, it's written down here, this and that, the other thing. So when we end up with the eigenvalues, very simply, and we have two kinds. One of them is going to be, excuse me, okay, if q is sufficiently small, because q, remember, q can be negative. Q can be negative because q is merely how much you change is a deviation from qc. So if this thing is negative, then this thing here is always positive. Okay? And so you have instability whenever q is sufficiently negative. Q being negative over here means that the wave number that you have is smaller than the desired one. It means that the wavelength is larger than the desired one. So this is what this is saying. The wave number is smaller than the desired one. The wavelength is larger than the desired one. And what happens is when the rolls bend, the wavelength decreases. That's to say, if you measure a distance, if this were straight, if you measure the distance between this and this, you would find that it would be greater than, less than the one that's bent like this, which is larger. There. And that is the zigzag instability. And it explains, the amazing thing is that all this is analysis after these equations have been way reduced down. But the Swift-Hohenberg equation has no such reduction. The Swift-Hohenberg equation, you saw, it's uniform in space, and it does this. It just does it. It forms these things, and nobody told it had. People told the NWS equation to do this. This equation was designed, but the Swift-Hohenberg equation was not designed to do any of these things, and it just does it. So this shows this is generic. You find this in all kinds of systems. It doesn't depend on the physics. It depends only on the symmetry. I mean, this can be an elastic sheet. It can be a magnetic field. It can be all kinds of things. Almost no physical features got put in here. Only symmetry qualities. Okay, so that's the end of this class. And I think John has printed out homework exercises, a homework sheet for the period doubling with 2 interesting homework exercises. One easy, one harder.